Hello and welcome to this Strong Learn video looking at applying Pythagoras' theorem to three-dimensional shapes. So here we have a prism, and we can see, and we're told in the diagram as well, that the cross-section of this prism is in the shape of an isosceles trapezium. So what it means by isosceles trapezium is that it has a line of symmetry down the centre. So essentially think of it as an isosceles triangle with the top cut off, and that's what isosceles trapezium is. So we're going to look at the length of the blue line. Okay, so if you watched the previous video in this series on Pythagoras in cuboids, we're going to go for a very similar approach here. So we're going to create a series of right-angled triangles. Now this one is a bit more complex than a cuboid, but let's look at our first triangle. So we're going to have to use the diagonal that we're looking for as part of it. So they should have come up the other way around. So if we look at this red one, okay, so this red one will work, but we don't at the start have any of those lengths. But if I create this this blue right-angled triangle, and in fact a third one because I need a green one, that's going to give me the missing height and the missing base of the red triangle. So do I have enough information to work with that? Well, let's have a look at what we've got. So let's just think about the blue one. So if I look at the blue one, I know it must have a base of 5. Now, how do I know it's got a base of 5? Well, if I look at the trapezium, I know the base of the trapezium is 6, and I know the top of the trapezium is 4. So there's 2 centimetre difference between the top and the bottom. And because it's isosceles, that must be equally distributed either side. So that means that where I've got this little strip missing on the right-hand side of the trapezium, that's 1 centimetre, which means the rest of it is 5 centimetres. Now the height of this triangle is much easier because that's just the full length of the prism, which is 12. So there we go, and then I can deal with that in a minute with Pythagoras. So let's look at the green one now. So the green one, what do I know about the green one? Well, I know that the length is 1 along the base, and I know the diagonal length here, that the hypotenuse is 4, because it's an isosceles trapezium prism, which means all of those slope lengths are the same. And I can see the one on the front left is 4, so all the others are 4 too. And then I might call that y because I'm using x for the blue triangle. So when I consider what I'm looking at with the red triangle, then the base of that is the value of x and the height is the value of y. So when I can identify x and y, I'm then in a position to find the diagonal length I'm looking for. Okay, so now it's just applying Pythagoras, and then we've got the working for that. Same again with the green one. Now I've left that as a third deliberately here, because when I come to use Pythagoras for the red triangle, I'm going to end up squaring it, and squaring root 15 gives me 15, which is quite nice. If I was going to give it as a rounded decimal and then I square that, I'm unlikely to get back to exactly 15. Alternatively, if you're doing this as a calculator exercise, you could store the value root 15 in your calculator's memory if you didn't want to keep it as a third. Okay, so now we apply Pythagoras for a final time, and we get our answer. Now we can leave it as a third, or potentially we can give it as a decimal. Okay, so there's some for you to have a go at. And there are the answers.